with the first presenter for this training session. It was about 13 years ago. I was at the Harvard School of Public Health, and I went to a talk by Jamie Robbins, and in that talk, as Jamie does, sort of work through a lot of equations, and he introduced this concept of doubly robust. I had never heard of it before, but he explained that it had a lot of interesting properties, and I spent some time after that thinking of how lost I was. So I'm thrilled that it's now taken only a little more than a decade to get a training in this topic by somebody who perhaps can speak the same language that I speak. So we have Michelle Johnson-Funk from University of North Carolina to talk about doubly robust estimation. And Michelle is an assistant professor at University of North Carolina, and she works closely with Till Sturmer and also with Alan Brookhart. And she's involved in as the core methods core for the Center for Women's Health Research at University of North Carolina. So, Michelle?
Thank you. Thank you for all coming bright and early. So as John foretold, I guess, this estimator has some interesting properties. I'm going to do my best to explain it in language that I, as an epidemiologist, understand. So if there's like an uber technical question, I'm going to have to call in the reinforcements, just to warn you. It's quite a pleasure to be asked to give this talk here today, and I'm really looking forward to hearing all the other interesting topics that you will be presenting on later. So without further ado, these are my disclosures. Most of my work in this area is funded by AHRQ. So just an outline. They did tell me I had 3 hours, so if this looks long, it's because I'm going to try to do a fairly thorough job here without boring you to tears. This is my goal. But just to get everybody on the same page, I'm going to spend a little bit of time first talking about causal inference and counterfactuals, and then some methods that we use to estimate effects, causal effects in observational data, or attempt to anyway. Then I'll introduce the doubly robust estimator, illustrate this doubly robust property, at least in an intuitive way, not the technical statistical sense, but and then talk about the assumptions, of course, how it performs if you do misspecify the models, present a macro that we've developed to help you implement it, although by the time we get to that point, you may be able to do it by hand, and then talk a little bit more broadly about choosing an estimator in the context of doing comparative effectiveness research and the kinds of properties that we would like to have for that estimator, and why the doubly robust estimator may be of interest in addition to some others. Can everybody hear all right? Looking at the back. Okay, great. So, causation versus association. This slide probably didn't need to be included, but just so everybody's on the same page, when we want to talk about a causal effect, this is the effect that we want to estimate from, that we would observe if we could intervene and change someone's exposure from one treatment or condition to a different one. And lots of times, of course, what we get when we do an observational study isn't a causal effect. It's a measure of association, and there's confounding or selection bias, or the thing that we're assessing is actually affected by the condition itself. So one of the classic examples that everybody gives is, we find that having matches in your pocket is associated with having lung cancer. Could we cause people to develop lung cancer by handing out matches? Probably not, I hope. So the counterfactual approach to this problem is thinking about what the expected benefit would be if we could intervene and change someone's exposure status. For instance, in this picture, the first individual who's a smoker who had a heart attack, we want to know if we could go in and change that person to be a non-smoker, would we expect them to still have a heart attack or not? We have a second individual here who's a non-smoker who did not have a heart attack. Could we actually use that second individual to stand in for what would have happened to the first person if we had been able to change their exposure status? Now, of course, the key question here from an observational researcher is this unexposed individual or population a fair substitute? Can we reasonably use that second person to stand in for the experience of the first? Probably not, at least not without doing some additional work. So probably the smoker is older, doesn't exercise as much, maybe weighs more. Of course, there are many instances of confounding that aren't this clear, and it's not entirely obvious whether you should control for some of the difference between the exposed and unexposed in observational studies. But what we need to achieve is exchangeability, at least conditional on the covariates. So exchangeability, that is that this second group can stand in for the experience of the first group if they had been in that other treatment condition. So how are we going to get there? Thoughts? How are we going to get exchangeability conditional on covariates? Zeb? We can adjust. We do it all the time. It's fun adjusting. You just put things in models and they magically make everybody close enough. Any of these look familiar? Could we use any of these things to try to achieve exchangeability conditional on our covariates? Propensity scores? Zeb thinks so. All right, sure, that's probably good then. How about G-computation? Ooh. No takers on that one. How about standardizing? Yeah. How about all of the above? Also a good choice. These aren't the only options, but these are several options. So interestingly, you can think of the doubly robust estimator as combining aspects of all of these approaches. And it does it in a, as Marie Davidian says, in a fortuitous way, so that as long as one of your models is correct, you'll get an unbiased estimate of the effect that you're interested in. So interestingly, our usual adjustment approach, putting everything in a single outcome regression model, does not necessarily apply to an identifiable study population in the presence of treatment effect heterogeneity. So that's something to keep in mind, and one of the reasons why we're interested in some of these other approaches. So just to go into these a little bit more as foundation work before we talk about how they are built together into the doubly robust estimator, there's the propensity score, which probably all of you are very familiar with. It's the probability of treatment given a set of characteristics or conditions. And you can use it to balance the treated and the untreated groups in terms of the risk of their outcome. And this is something that we can observe or estimate from the observed data. And in fact, we do better if we estimate it from the observed data rather than going out and finding a quote-unquote true propensity score. So briefly, just a little SAS code for the geeks in the audience, and I apologize to Stata and R users because I don't know either of those. If you had a small enough number of covariates and they were categorical, you could just calculate by hand the propensity score. You could look within each unique combination of characteristics and say, well, what's the probability of treatment within that tiny little strata? Normally what we do, because we have lots and lots of covariates and we have some of them that are continuous, we estimate this using logistic regression. So something like the SAS code that's here. And in the final line of this little procedure is where we can output the predicted probabilities. So those are the propensity scores for each individual in our data set that get spit out, and then we can use them. There are other ways to estimate your propensity score if you like. I haven't seen compelling evidence that any of them work dramatically better than logistic regression, but they may be interesting in some settings. So what are you going to do with this propensity score once you have estimated it? So one thing that you can do is weight your observations by the inverse of the probability of the actual treatment that they got. So what does that actually mean? If you are looking at a person who was treated, then the inverse of the probability of the treatment they got is 1 over the propensity score. If you're looking at a person who was untreated, then the inverse of the probability of the treatment that they got is 1 over 1 minus the propensity score, because normally you model the propensity score as the probability of treatment, not as probability of not being treated. So you have to do 1 minus the propensity score. So the nifty thing about this approach is that after you've weighted your sample accordingly, you should be able to just take the crude effect in this pseudo-population that you've created by weighting your observations, and that should be unconfounded. So just the straight-up crude estimate after the weighting should be unconfounded. And the nice thing about this is that you can estimate then a risk or a difference measure or a ratio measure. You're not constrained in quite the same way as we normally are by using our a logistic regression model and getting an odds ratio. So this effect estimate is estimating the effect of the treatment in the total population. And we'll talk some more about what are the populations that we're interested in. And there are probably many settings where we're interested in something other than the total population, but we'll talk more about that as we go. Of course, key to this is that the propensity score model must be specified correctly. So if you did a lousy job of building a propensity score, you're not going to manage to achieve this state of exchangeability between your two groups in these pseudo-populations, and you're not going to get an unbiased estimate. So another approach that also uses the propensity score are SMR weights. And I don't know about you, but this was, day 3 in epidemiology when you handed a table of data and they said, okay, well, why don't you standardize that too? And I hadn't heard much about it since then, to be perfectly honest. But another way that you can use the propensity score is essentially as an SMR weight. And so if you want to weight your treated observations by 1, they just count for themselves. And then your untreated individuals get weighted by the propensity odds. So the propensity score over 1 minus the propensity score. So now we're getting a treatment effect that is applicable to the treated population, not to the total population. And again, the risk is just the observed risk in the treated group, but you can also get a risk difference or a risk ratio. And again, it assumes the propensity score model is correctly specified. So just to give you a sense of how these two different approaches give you different populations that you're making inference to. So these are the propensity score distributions for initiators in the blue, non-initiators in the pink, and then the total population is the yellow. So if you were to apply the propensity score in these two different ways, you can either use it to weight inverse probability weight or to SMR weight. And you can see then looking at how your sort of pseudo-populations that get created from there differ. So the IPTW one resembles the total population, our yellow line, and the SMR-weighted one resembles our treated population. You see that? So one inference you could make if you get different answers from these two approaches is that there may be important treatment effect heterogeneity here. And because you are weighting your sample to different target populations, you're going to get a different average treatment effect because they're in different groups of people. So G-computation. How many people have ever heard of G-computation? Whew, not bad. Wow. I think they might mostly be at Harvard, though. So G-computation, you can also think of this as marginalizing your treatment effect. So normally what we would do if we do a outcome regression model and throw everything in is then we would take our beta, the beta estimate that we get out of that model and exponentiate it and say, lovely, look at my relative risk or my odds ratio or my hazard ratio. That alternatively, you can do what's called marginalize that effect. So you can take the entire population and kind of push it through the meat grinder of your betas, with their covariate values, observed covariates, and you can spit out for each individual what would have happened to that person had they been treated or untreated based on the results of fitting my outcome regression model and whatever covariates they showed up with. We don't normally do this. It has some problems in that it can extrapolate beyond the sort of range of where your data actually live, and you need to be careful of this. But it does potentially offer some nice features. So unlike our normal approach, you can get the risk out. You could get a risk difference and a risk ratio or an odds ratio. You can calculate whatever you want because you have an outcome for each individual that you can then use to, once you've taken the average of them in the two conditions, you can take the difference or the ratio, whatever you like. And likewise, you could select different groups within the population so that that estimate applies to the total population, the treated, the untreated, a group that has an interesting comorbidity. Again, like our other approaches, this assumes that our outcome model is correctly specified. So everything that we're doing is built on this assumption that we didn't screw up when we built our outcome regression model. So briefly, and the reason I'm giving you a little bit more detail about what these methods actually look like when you implement them is when we get the doubly robust estimator, it's going to build on these, and I think it's a lot easier to get it if you have more of a gut sense of what the pieces are doing before we start. So if you wanted to do the G-computation, you could, in SAS, just create a stacked data set with 3 copies of everybody. And in one copy, you're going to set their treatment to 0. In another copy, you're going to set their treatment to 1. And then the third copy, the original, you're going to use that to estimate your regression model. And then for all the copies where you set their treatment to something, you're going to set their outcome to missing so that you don't inadvertently use them again and again and again to estimate your effects. So then you fit a regression model, and much like we did with the propensity score, you then have it output the predicted probability of the outcome for each individual, for each copy of each individual. So then you have these counterfactuals for each person in your data set under both treatment conditions. And then those can be used to calculate the mean response in the treated. Well, the mean response had everyone been treated, again, assuming that you got your model correctly specified. The mean response had everyone been untreated. And potentially you can go in and start looking, if you fit a very flexible outcome model, you can look for instances of heterogeneity. So you can say, well, when I fit this outcome model with lots of interaction terms and allowing things to be very flexible, I can see that maybe there's an interesting difference by age or sex. And you could, of course, identify that looking at the betas as well, but you'd have to do it separately from estimating your overall effect. So this brings us to doubly robust estimators. This was a kind of a by the chance finding of Robbins and colleagues in the mid-90s. They were working on the inverse probability weighted estimator and realized that it wasn't particularly efficient. And so they were working on figuring out ways to make it more efficient so that you would get nicer standard errors out of it. And they found that if you threw some extra stuff in after the normal inverse probability weighted bit, you could improve its efficiency. And eventually they realized that this particular form of extra stuff that you could throw in there was optimally efficient for this estimator. Only later did they realize that it was doubly robust, and that by throwing this extra junk in, you could not only improve the efficiency of the IPTW estimator, you could make it doubly robust so that you could misspecify the IPTW estimator or the propensity score side. If you got the outcome regression side right, you still would have an unbiased effect estimate. So 2 models, actually 3 if you're going to count real close. At least for this particular estimator, doubly robust estimator, we're going to fit a propensity score model. Just usual propensity score model, then we're going to fit 2 outcome regression models. We're going to fit one among the treated and one among the untreated. So our treatment variable is actually not going to be in our outcome regression model because we're going to be fitting those models within those groups. And these 2 different sets of models can have different covariates, different parametric forms. And as I said, if either is correctly specified, then this estimator is unbiased. So I don't know about you, but this gives me seizures. So this is the point at which we're going to make this understandable, I hope, to non-biostatisticians. And I hope I don't mangle it too badly. But Marie Davidian at NC State was very kind in sort of translating this for my benefit. So I'm going to try to portray her translation accurately. So the first half of this equation is the average response if everyone in the population had been treated. And the second half below is the average response if everyone had been untreated. And in this case, we're taking a difference between the 2. So we're getting the mean difference. So if we had a continuous outcome, you can imagine that the outcome is, lipid levels at 1 year of follow-up. And this is going to be a difference measure, but it could equally be a ratio measure if you took the ratio of the upper and the lower quantity. So let's put this into sort of epi notation as opposed to stats notation and see if it makes a little bit more sense. So this is the first row here is the general form of the equation. So the first one is for a given individual, the way that we calculate the response that we would expect that observation to have in the presence of exposure. And then the second column is the response that individual would have based on this estimator without exposure. I still have a little trouble making sense of this. So let's fill in the 1s and the 0s. So if we're looking at an x equals 0, we're talking about an unexposed person. And if you want to fill in the x's with 0s here, can somebody tell me what the first component of that equation reduces to? 0? And how about the second component if you fill in a 0 for the x?
It's minus times minus y.
Right. So y1 here with the hat on it is our estimate from our outcome regression model among the exposed. So if you are somebody who's unexposed and your x is 0, that whole big mess right there is just going to boil down to whatever our outcome regression model among the exposed people said you were likely to do if we had given you exposure. So you weren't exposed. We don't really know anything else from your experience about what was likely to have happened if you had been exposed instead. So we're just going to use the regression model among the people who really were exposed, and we're going to trust that that's the best we can do in this context. And then conversely, for the people who actually were exposed, if we want to sort of give our best guess of what would have happened if they had not been exposed, if you want to fill in the 1s for the x's here, hopefully you will also find that that boils down to just the result of our outcome regression model among the unexposed. Yeah?
So the dr1 is a numerator in the previous equation. dr0 is the denominator?
Correct. So, yes. The top half of this, these actually aren't numerators and denominators because this is a minus, so it's a, but they were stacked on top of each other, so I can understand the confusion that I created there. So the other two are a little bit trickier, but I know you can do it. All right. So let's start with estimating what we're gonna use for the expected outcome under treatment but for someone who actually was treated. Now, at some level, you might say, well, they actually were treated. Why do we need to estimate anything here? We'll just use that. Well, the trick is that we don't want, like an IPTW estimator, we want to weight them such that they can stand in for what would have happened to some of those untreated people. And they're not the same people as the untreated people, or we could just take the crude effect and be done. So we have to do some weighting here. So looking at the first component of that term, y sub x equals 1 over the propensity score, does anybody recognize that quantity? Does it look familiar to anybody? The first term in this equation. Yeah, that's right. So this is y sub x equals 1 is what we observed that individual to actually experience, and we're weighting it by 1 over the propensity score, which is exactly the IPTW estimator. So, yes?
Can you repeat the questions once they answer that?
Thank you. So Alan asked if this was the IPTW estimator, and that's my understanding of it in any event. So the second component of this equation is a combination of what we got from the outcome regression model among the people who were exposed and something else, 1 minus the propensity score over the propensity score. What does that look like? Anything that we saw earlier, maybe?
The weight for the untreated?
If you were doing an SMR, if you're doing a standardized morbidity mortality ratio and standardizing to the untreated, that's what this second bit would be, the weight piece of it. I promise this will get more clear in a moment. But I want you to recognize where the building blocks are, and then in a minute we're going to go through and look at how it manages to be doubly robust. Okay. And then lastly, for the folks who were actually untreated, what we're going to use for them for their estimate of the response without treatment is analogous to what we just did in the treated, but you have to flip things over or do 1 minus. So is that clear enough? So here, instead of using 1 over the propensity score, we're going to use 1 over 1 minus the propensity score. So that's the same as what we would do for an IPTW estimate. And the second piece of this actually is our sort of classic SMR weight. Okay. You weren't expecting an exercise, were you? Okay. So we're going to just try to do a quick hand calculation, because this is going to be, you're actually going to realize that you don't need a macro if you do this. So I'm going to hand out a couple of pieces of paper. So let's imagine that we have a simulated population of 10,000 people. Our quote-unquote observed treatment, it's a simulation, so we didn't actually observe it, we just made it up, is denoted with X. It's either 0 or 1, it's dichotomous. And then our quote-unquote observed outcomes are also dichotomous, and we're going to have 3 dichotomous covariates. So this is actually the situation in which we don't need to do any models, actually, because we can just calculate within the unique strata what these numbers are. So our crude relative risk is 1.4, but because we simulated the data, we know that the truth is null. So there is no association. And likewise for the risk difference, it's also null, of course. Okay. So if we're going to figure out, if we're going to calculate this doubly robust effect estimate, what are the ingredients that we need to do this? We're going to need a propensity score. We're going to need the predicted outcomes a la G-computation under each exposure condition. And then based on that, we're going to put those together and get what we think would happen at the individual level under each condition. So I've put the simulated data together in tabled format so you can see exactly all of the people. So here are 3 covariates, Z1, Z2, Z3. And you can see our among the unexposed, the number who had the outcome, the number who didn't, and the total, and then likewise for the exposed. So using this, we can calculate all the things that we need that I just talked about. So let's focus on just the column of people who have all of their z's equal to 0. We could do it for everybody, but we'd be exceedingly bored by the time we got through this. So I think just doing it for one might be enough. So for our individuals who had all of their covariate levels set to 0, how would we go about calculating their propensity score for that unique combination of covariates? What's their propensity score going to be? The probability that they were treated, that x equals 1, given their values for z, so that's everybody in this column has the same value for z. So how many treated people did we have? We had 2160, correct? Okay, and total 3960. Right, so we just divide. That's our propensity score. So conditional on these covariate values, that's all the propensity score is the prevalence of treatment within this little unique combination of characteristics. Now, obviously, if we had a continuous variable like age and we didn't have infinite data, we would use a model instead to do this. But we wouldn't have to in this circumstance. So what else do we need? We need to try to estimate what this G-computation type outcome is that comes out of our outcome regression models. So that one's not too terribly complicated. So for the state of being unexposed, what would have happened if you were unexposed and you had all of your Z variables set to 0? We're just going to use this level, the probability of the outcome, or the number of individuals who had the outcome divided by the total group. So that would be your predicted probability. If you happen to be unexposed and you had all of these covariates, this is what we think our best guess is of your probability of having the event in this little group. Okay. Now, how about the analogous quantity for Y1? If we had exposed individuals. Louder?
432 by 2160.
Okay. Ta-da! Okay. So that wasn't too painful. Does this make sense? Am I losing anybody yet? I mostly see nodding, and there's nobody snoring yet, so I'm happy. Okay. So now we have to get, based on those ingredients, now we want to figure out what our sort of best estimate is of DR1 and DR0. And we need all those ingredients that we just calculated in order to do this. Okay? So let's start with an easy one. Let's start with DR1 under the condition of not being exposed. So this is DR1 without exposure. Does anybody recall from the last slide or your slide deck? Point 2. Way to go, Alan. Okay. That one was pretty straightforward. All right. So what about under this condition? Oh, sorry, just a sec. I got to back up a slide. My apologies. All right. So now under DR1 for exposure, we actually have to calculate two different things. I mean, we wouldn't really the equation doesn't care, but because we're going to do it by hand, it's plugging in two different numbers for y. So if we're looking at an individual who we're saying was exposed and had the outcome, how are we going to put together their information about their actual outcome and what we are predicting their outcome would be if we did a regression model and estimated it? So we need a combination of our propensity score, which was 0.545, if I'm remembering right. Yes. And then we need the propensity score over here again, and this predicted outcome, not from a regression model in this case, but just from our hand calculation in that little mini strata. Everybody brought their scientific calculators with them, right? Okay, that's okay. So, not real hard. Do you want to give it a shot to do DR0? Or is this so evident now that it's not interesting? So if we were going to estimate this quantity here, what do we need? So pick one. Yes. So we're going to use the 0.19 from this slide. And then we're going to do essentially the analogous work down here that we did to get DR1. So now we've done this for a couple of individuals, one that had the outcome and one that didn't under both exposure conditions. But these are just estimated or calculated at the individual level. This isn't a population level quantity yet. We're going to have to sum up over everybody in order to get the average under both conditions. So then once we've averaged these, then we can calculate a ratio or a risk difference, or we can just take the absolute risk, the average risk, either under exposure or not, depending on what the effect is that we're most interested in, given the research question. So now I want to dig a little bit deeper into the more statistical notation. And if anybody is prone to seizures, look away. I'll let you know when it's safe to look back again. This is the prior exercise makes it clear that this isn't that complicated to calculate. You could code this up in SAS now, I suspect, if you do any programming at all. But it's not evident to me, looking at what we just did, why that is doubly robust. Not at all, actually. It just kind of looks like everything in the kitchen sink thrown in together. So that's why we're going to do this next section. So hang tight. So this is the notation that we're going to use here. So yi is our observed outcome. Xi is our binary treatment. And then we have, we're just going to say an array of covariates that we're going to denote with a bold Z and a subscripted I. Then we're going to have a model that we fit to try to estimate the propensity score. Sorry, this is the true propensity score, and no, I'm getting it backwards. This is the estimated from the model. And then we have two regression models that were fit within each level of exposure. So then we have the Y1 and Y0. Those are the result of our regression models. Those are our predicted outcomes in the presence and absence of exposure. And we're going to say for the moment that we want the risk difference as our causal effect of interest. So here is the big scary equation again. The causal effect that we're going to try to estimate is the difference in the mean response if everyone in the population had been treated versus everyone had been untreated. So let's pick this apart a little bit and see if we can figure out where this double robustness is hiding. So let's just focus in on the estimated response if everyone had been treated. So that was the top half of what was on the prior slide. The same logic is going to apply to the if everybody had been untreated, the lower half. So as we saw before when we were working through the sort of epi version of the notation, this first section is just an IPTW estimator. So it's the observed response weighted by 1 over the treatment that they got. And Jamie et al. Call this second bit the augmentation. Why they call it the augmentation, I don't know. There must have been a better word they could. In any event, it makes the estimate more efficient, and it supports this doubly robust property. So this extra little bit is really key, and that's where we need to dig in to figure out where the doubly robust bit is lurking. So let's take this. Now, if we had the first section as an IPTW estimator, well, that's an estimator that we use. That all by itself should be just fine. That estimates the quantity that we want, at least if it's correctly specified. So what we can do is sort of rewrite this as the expected response under treatment plus a bunch of other stuff. So we're going to keep the augmentation over here, and we've just rewritten this a bit so that we can see more clearly where the interesting parts are. So let's focus on that bit, because if we have here the estimate of the response with treatment, then we just need to get the rest of this to reduce to 0, right, to get what we want. If the thing that we want plus 0, that would be unbiased, I hope. So we're going to work through 2 scenarios here, one in which our propensity score model is correctly specified, but our regression model is not, and then a second in which our propensity score model is incorrectly specified, but our regression model is correct. So that's where, that's the promise of the doubly robust estimator, is that you should be able to get it right in one spot and be home free. So first, let's see what happens if our propensity score model is correctly specified, but our outcome regression model among the exposed is not. So this is the portion of that augmentation that represents our propensity score model that we've fit. So if that was estimated correctly, then we can make this substitution in this equation. So that's estimating the thing that we actually want it to estimate, thank goodness. Our regression model over here is not. So when we go to make the substitution in this equation, we're going to be stuck with this original quantity, which is not what we wanted it to be. We estimated something, but it was not achieving what we wanted in terms of exchangeability for the covariates. But on this side, we have achieved what we wanted with propensity score, so we can make this substitution. So having done that, we're going to manipulate that equation after the substitutions, essentially algebraically, and you're going to have to trust Marie Davidian on that. And then in this last section, we have to invoke the assumption of no unmeasured confounders. And this is fairly key. So the fact that this estimator is doubly robust does not get us out of having to measure all of our confounders. I'm sorry. If you were thinking that this talk was going to be about how we don't have to measure everything anymore, I guess I probably should have mentioned it up front. So when we can assert that we don't have any unmeasured confounders, then we can make this substitution, and then something really interesting happens. This first quantity reduces to 0. So this minus this divided by the same thing, 0. And we're going to multiply that times something. It wasn't the right outcome regression equation. So essentially it's a bias term. But we're going to multiply 0 times the bias term that was left over from our outcome regression model, and it's going to cancel it out. And this augmentation is going to reduce to 0 then. So now we can do the same thing in the opposite scenario. So where we have our propensity score model incorrectly specified, but we managed to get our regression model among the exposed correctly specified. So same story, but this time we cannot make this substitution that we made before. On the regression outcome model side, we can. And then we're going to manipulate this set of equations to sort of convert it from this into this form. And at that point, again, we have to invoke the assumption of no unmeasured confounders. And again, the product of this term that reduces to 0 is multiplied times the leftovers from our poorly specified propensity score model, and we end up with an augmentation that's reduced to 0. So what do you think would happen at this point if they were both misspecified, if that did not reduce to 0? It'd be okay anyway, wouldn't it? I mean, we don't really, probably be close. Probably, maybe. You can imagine that if you really badly specified everything, you're now going to multiply two bias terms times each other, and it could get bigger instead of smaller. So this is something to be keenly aware of in this context, that this is not any kind of magic bullet. And done poorly, you can end up in worse shape than you would have been if you had just done one crummy model. Okay. So if you've been tuning out for fear of medical consequences from looking at statistical equations, you can come back now. Basically what all that boils down to is that this gives us the quantity that we're interested in plus some augmentation, plus the other quantity that we're interested in plus some augmentation, and all the augmentation is going to reduce to 0 as long as one of the two equations got correctly specified. Okay. How are we doing? That was a little heavy duty, but is everybody roughly with me? Okay. Nobody wants to admit that they have no clue what I just said, but that's okay. I'm going to go through assumptions here, and then I think we're ready for a break. So, of course, you'd like some assumptions with that estimator. Of course, we need exchangeability, just like we do when we do anything else, except maybe an IV. So we have to correctly specify at least one of the models, and in order to do that, we have to have measured all of our confounders. We need positivity. So again, sort of from the same vein as our normal propensity score methods, if we have regions of people who don't overlap and are just can't be made comparable because they simply are not. I guess the way to think about this is if your treated population were women over the age of 50 and your untreated population were men under the age of 50, there is nothing that this can do to rescue you from that dilemma. Consistency is another assumption that we have to invoke whenever we do sort of methods related to causal inference in general, and that just says that the models that we build give you estimates of the outcome that are consistent with what the actual observed outcomes were, and then no interference, which we mostly try not to think about. But if you're doing, infectious diseases, or you have people whose outcomes are affecting other people's exposures and outcomes, then you could be up a creek. But these aren't novel to this estimator. This is just part of the package of what we have to do every day. So I'm going to invoke a break, and the folks on the phone give us about 15 minutes to let everybody get up and stretch, and then we'll come back and continue. Okay, I think we're going to start diving back in. if you need to increase your glucose levels before we start again, the non-federally provided Swedish Fish and Smarties are on the back table. Okay, so now that you have a better idea of what this thing ought to do, let's find out what it actually does when we set up a simulation and test its behavior. So first of all, what if the model is misspecified? So the whole point of this is to be able to misspecify one of the two models and still end up in good shape. But what actually happens if you do that? So Lunsford and Davidian published a nice paper where they compared lots of different estimators, the doubly robust estimator among them. And because they simulated the data, they knew what the true association was that they were trying to find. And then they varied different parameters. And then what they did to misspecify the model was they omitted a confounder from the outcome regression. So this is pretty extreme. You wouldn't do this, would you? I mean, you wouldn't put it in the propensity score model. You wouldn't measure it, put it in the propensity score model, and then just not bother to put it in the outcome regression model. That said, this is a test of can it hold up under extreme misspecification. Okay. So in that case, they were very pleased to find that, in fact, it's basically doubly robust. You still get an unbiased estimate, whereas if you misspecified your outcome regression model and that was the only thing you had to work with by leaving out one of your confounders, then you would end up biased, roughly in their special simulation in the 10 to 35% range. So it's a simulation. They controlled all of the parameters and the associations, and they could have made it much worse or not as bad, of course. But at least in relative terms, if you compare how the doubly robust estimator did to our normal approach, it looks like it's doing okay. And then the other sort of way to assess how well this is working is by looking at our 95% confidence interval coverage. So for the doubly robust estimator, we came in at around 93 to 96%. Of course, for 95% confidence intervals, it should be pretty darn close to 95%. And then because of this bias that we were getting in the maximum likelihood estimator, and we didn't have anything else to work with, our whole estimate and the confidence intervals around it shifted enough that it no longer included the true value. And you can imagine in sort of the world where you deal with lots and lots and lots of data and you have ridiculous amounts of precision, this isn't such a surprise because you move your estimate just a tiny bit. It's very precise, and lo and behold, the true effect estimate is no longer contained in that interval. So, again, in this setting, we were still in this situation where there weren't any unmeasured confounders. The propensity score model was correctly specified. So just to be clear that they didn't do something magical here where they didn't have to include a confounder somehow, somewhere. So let's talk about a different scenario that maybe isn't as unrealistic, misspecifying covariates. So you measured them. You put them in both models for your doubly robust estimator, but we don't really know the true form of the relationship between, say, age and the risk of the outcome. So we do the best we can, but let's say that instead of putting in age as a continuous variable, which in these simulated data was the true association, we put it in as categories because those are really nice to report. You get like a relative risk for each age category relevant to some referent. It actually kind of makes sense to people as opposed to the log odds increased by 0.1% for every year increase in age, but nobody can figure out what that means anyway. So we make these nice categories, and they look great in our tables. But if there's actually a continuously increasing relationship, then we're going to have residual confounding within each of those categories. So again, it's a simulation. We know what the true relationships actually are, and we misspecified it by using these categories in the outcome regression model. And then we included it in the correct form, in a continuous form, in the propensity score model. So again, we basically find the same kind of thing qualitatively, just not as extreme in general. It's all a function of sort of how you set up the simulation. But in relative terms, the doubly robust estimator was unbiased. The maximum likelihood estimator was biased depending on how strong the risk factor, like age, was. And again, the confidence interval coverage looked fine. Now, one thing to be clear about here is there is a price to pay in doing this doubly robust estimate. There is some loss of efficiency. It is not as efficient as a single correctly specified outcome regression model. No free lunches, definitely not here, but not with the doubly robust estimator either. So the standard error for the doubly robust estimator is actually going to be a little bit bigger than what you would get from a single correctly specified maximum likelihood sort of standard regression model. That said, because of the bias, if you put together the bias and the efficiency together, you can look at the root mean squared error, which is basically how far off are you on average under that whole distribution. And taking that into account, then it's clear that the doubly robust estimator is still doing better than the maximum likelihood in this particular scenario. So again, we're still in the land of no unmeasured confounders, just to be totally clear. Now, what happens if both of them are misspecified? So we had something like age, and we put it in as categories in both the propensity score model and the regression model, the outcome regression model. I guess you can read the slide as well as I can, but what do you think is going to happen? Will it be unbiased at this point? Oh, of course it will. It's doubly robust. It can do everything. No, it's about the same now as the maximum likelihood estimator, and you still have to pay the efficiency price. So now you're actually going to do worse than a single badly specified outcome regression model. Okay? So it's, there has to be a price to pay. If you're going to do a thoughtful job of building your regression models, you're going to have to do it as thoughtfully for both of them in the doubly robust estimator now. It's not really, two chances to get it right if you just kind of throw stuff in one of them and don't try to actually see that it's fitting well. So it provides some protection against misspecifying one, but not both of your component models. That said, the residual confounding that you're going to have from misspecifying a covariate, because you're not going to just leave it out of the model completely, is pretty minor in magnitude compared to the size of the bias that was originally there when you didn't have it in at all. And you can end up with an estimate that is more biased than a single misspecified outcome regression model. So you remember where we saw that those two terms are going to multiply together. So you could potentially magnify the amount of bias if you did a really bad job on both ends. So it is nice to get this sort of second chance at building a really good model, but you still have to do it carefully, check for violations of assumptions, just like you would do for any other estimator. So I'm going to walk through the macro that we have available for implementing this. Again, to be honest, now that you've done the hand calculation, I bet you could do it yourself. The only real benefit to this is that it automates the bootstrapping process so that you get appropriate standard errors. So, if you're not a whiz with bootstrapping, then it's easier to use this. But that said, there probably are things that you would want to check out anyway on your own. So anyway, it would be fun to play with maybe because, we're geeks. We play with things like that. All right. So this is what the sample code looks like. And one of the things that we wanted to do when we developed the macro was to try to make it look like a SAS proc instead of like your standard macro, which is almost unintelligible. So there's some stuff here at the beginning that does not look at all familiar. But after that, we tried to sort of mimic SAS speak. So you provide a data equals statement to tell it what data set to use. You put in the descending option to model the probability of 1 instead of 0. And then WT model is your weight model. So the dependent variable there is going to be your exposure, and then whatever covariates you want to put into your propensity score. And there aren't really any other options here at the moment. Someday, when I run out of other things to do, my hope is to implement just the plain vanilla IPTW estimator and variations on propensity scores so that you could easily compare all of those in here. And then this is your outcome regression model. And remember, this is going to be done within levels of exposure. So you don't want to put the exposure in on the predictor side of this regression equation. And then down below is what you're going to get out. So you'll get an estimate of the average response had everyone been untreated, the average response had everyone been treated. Then delta DR is the difference. It gives you the log of the relative risk, the log of the odds ratio, and then those two in their native forms. But remember what we did before, this is all based on at an individual level having calculated each of these things. So we can put them together in whatever different forms we want to. Now, the standard errors that you're getting here, don't trust them. These are based on an equation that assumes that both models are correctly specified. And as a very kind reviewer of my paper noted, it wouldn't really be doubly robust if your standard errors weren't doubly robust. So bottom line, before you report anything, you definitely want to bootstrap your standard errors. These are going to be probably in the right ballpark, and because the bootstrapping takes some time, I wouldn't turn it on the first time you ran it. But, when you get to the point where you're ready to find out, okay, really, what do these numbers look like? Then you can add this bootstrap option. You can tell it how many iterations you want it to do, what alpha you want to use, and then it can output the resulting data set with, one estimate per iteration into a data set. So then you can analyze those if you want to do something on your own later. And when you turn on that bootstrapping option, then you're going to get this additional output. So this is going to report both, these are the medians and percentile-based confidence limits in the lower part here. The upper part is going to give you the empirical standard error based on the distribution of those estimates. So in each iteration, quick bootstrapping refresher course, you're going to do 1,000 iterations of this analysis, each one on a resampled data set from your original data of the same sample size. It is going to estimate your effects, and then you're going to end up after 1,000 iterations with a whole distribution of those effects. So then you can take the mean of that distribution, you can take the standard deviation of that distribution as an estimate of the standard error, and calculate confidence intervals based on that. Or if you think there's something that's not strictly normal going on, if you have a distribution that has a long tail or something squirrely about it, then you can actually use the percentiles. So these are based on the 2.5th, the 97.5th percentiles of that distribution and the median. So this is where you can download it. Email me if you have any trouble using it, but it hopefully, knock on wood, works. So this is just showing how you might specify the models for an actual analysis. So you'd have your treatment variable, a bunch of covariates that you're interested in, and then there's this option here called Show Curves. So one of the things we wanted to do was to include some of the diagnostics that probably we should all do whenever we do any analysis. So this is going to show you the propensity score distributions stratified by the treatment group. So you can actually look at them and see, oh, this is totally hopeless. I have 50-plus-year-old women, and I have 50 and under men, and we can just all go home now. The other thing you can do is ask it to trim your data to the area where you do have common support. Again, probably something that we should all be doing anyway. So there's a common support option, and you can specify something like 0.9, and that will keep the 90% of your data where you have common support in the middle, and it'll get rid of 5% on either end. And Tilstromer has a nice paper that talks about how that may help to address people who are treated contrary to prediction, which is sort of a symptom that you get from an unmeasured confounder. So I just said an unmeasured confounder. It's not going to cure that problem, I promise, but it's an interesting diagnostic to check and to see if your effect estimates start to move around when you get rid of those people. You might be a little bit worried then. Then you can also, because you've calculated all of these things for the individuals, you can go in and check and see, well, if I just look at all the women, what do their effect estimates look like? If I stratify by age groups, do I see treatment effect heterogeneity based on that? To some extent, this is a function of how flexible you make those models. So if you allow your outcome regression and your propensity score models to have a lot of interactions and higher order terms, the nice thing is you're not going to have to interpret those individual betas because you're going to marginalize the effect over everybody. But you can incorporate that flexibility in the model development so that if you go looking to see, is there an interesting sex difference here, you might be able to pick it up. So the code creates a bunch of temporary data sets, which may be of interest to you. It normally deletes them so that it doesn't inadvertently use them in the next round if something goes wrong along the way. But you can go into the macro and just kind of turn off that part so that you can go and investigate them yourself, or you can add a little bit at the end to have it save it as a permanent data set. So then these are the data sets that have the results of the bootstrapping, and there's some diagnostics there for the outcome regression models to see if they're basically outliers, if there are weird people who are getting very extreme values that you may need to be worried about. So I guess we talked a little bit about diagnostics, using the common support option, looking at the propensity score distributions. Again, these are things that you can do on your own. This isn't, particularly complicated SAS code, but it can be convenient to just sort of let it run and see if there's anything of concern there before you get super excited about your odds ratio of 6. Okay. Practical considerations. How to know which covariates to include. So just based on everything that you knew before you walked in today, which covariates should we include in our propensity score model? Everything that's predictive of the treatment, of course. No? All right. Any other suggestions? If we put in something that gives us a really good C statistic for our propensity score, perfectly predicts who gets treated and who doesn't, is this a good thing? You don't look happy. Is there anybody else who's unhappy? Yeah, tell me why. So to repeat for the folks on the webinar, you need some random variation in there. You need some people who could have kind of gone either way, some of whom were treated, some of whom weren't. That's kind of the basis of all of this. And if there's something that is not actually a risk factor for the outcome, but is really good at predicting who got treated, then that's an instrument. And if we put it into this propensity score model, it's going to separate our propensity score curves very nicely and give us a beautiful C statistic. And we won't be able to do anything after that. So what about in the outcome model? How do we feel about what ought to go in there? Should it be only the confounders? Should it be anything that's a risk factor? Do we have strong feelings here? Everything in the kitchen sink?
Same set of covariates you use for your propensity score model.
Okay, so we have one vote for same set of covariates that you used for your propensity score model. Why would that be?
Well, I mean, the objective for the propensity score model is that's for confounding, and that's what you want to do in your outcome model. Same set of covariates.
To recap, so the goal here is to adjust for confounding. That's why we're doing this. We don't actually want to be able to accurately predict who exactly got treated. I would say that it's fair to include risk factors for the outcome, even if you don't have an a priori reason to think they might be driving treatment choice, because they might be imbalanced by chance in your data. But yes, in general, I think it's probably the same set. It's all of the stuff that you think might be confounding the association that you're interested in. So here's another practical consideration. What do we do when we get these results from our real study in the real world, where we didn't simulate the data, and we have no idea what the true value is, and therefore we don't know what the bias is? No, really, what do I do? I don't know. This is not it is not obvious at this point what you should do. At some level, you could argue, well, let's see, our maximum likelihood estimate is pretty close to our doubly robust estimate, and it's going to be more efficient. So in terms of, like, even if you thought the doubly robust estimate was better, in terms of root mean squared error, you might do better with your maximum likelihood estimate. Maybe they're both wrong. Maybe my outcome regression model and my propensity score model are wrong, and just by chance I get something for the doubly robust estimate that's close to one of them. So, I mean, this is, unfortunately, this is a genuine question. It is not entirely apparent what to do in this case. I think the best thing you can do is what we already do, which is to try to understand where the variability is coming from. Why am I getting a different estimate from one of these than the other? And dig into it. That there isn't like a nice formula to wrap these all up together. On the other hand, Mark, when he gives his talk tomorrow, might have some better options for us for dealing with multiple ways of estimating our effects and pulling those all together. So just in terms of the macro at this stage, there are some frequently and frustratingly asked questions. It can only handle, the macro that I just showed you can only handle binary exposures and a binary or a continuous outcome. So that's not a small problem in our field, where lots of times we do not have the same amount of follow-up for everybody in our study. I have somebody who was disenrolled from their health plan on the day after their surgery, and I have somebody who was followed up for 10 years. And I don't really want to throw out 10 years of data for one person and lose what little I have for everybody else. So this is a challenge. Again, in my dream world, I would love to work out with a smart biostatistician the sort of Poisson implementation, so that at least we could deal with incidence rates, and I would feel confident that I had done it correctly. The macro that we have doesn't recognize, even though it looks like SAS Code, it's not actually a SAS proc. So it can't do all of the magic that SAS procs do. So it can't recognize a class statement or a where statement. and those interaction terms and polynomials that you want to put in your model so that it's beautiful and flexible, you have to make all of those in a data step before you get to this part. So sort of in the last phase of this, I want to come back to the bigger picture of what we're trying to do and how we might think about what kind of estimator to use in our work. So we're dealing in the world where we have possibly millions of individuals in our data sets, hundreds of covariates or more, imperfect confounder measurement, to say the least, and strangely very precise estimates that probably mask to a great degree the uncertainty that we really have in those estimates. So it looks like we know that the effect estimate is 1.12 and certainly not lower than 1.1 or higher than 1.4, and that's just not the case. We're also in the situation where comparing active treatments, the real differences that we are looking for and that would be interesting to us are very small. A 10 to 20% difference in active treatments is not uncommon. And those can be meaningful if there's a common effect or a very serious outcome. So it's they may be clinically relevant. So thinking about the effects of residual confounding and model misspecification, unfortunately, we're living kind of in the perfect storm of where residual confounding could be pretty unpleasant. So the real differences that we're interested in are quite modest, and it doesn't take a lot of residual confounding to move that effect from a true estimate, say up here, down to the null. And, those are pretty modest changes, but because our estimates are so apparently precise because of the vast quantities of data that we're using, at least until the meta-analysis comes out 4 years from now, you might believe that there is truly no difference between these two treatments that you're comparing. There's also the opposite problem. So your residual confounding can move it away from the null. There may truly be no difference between these two exposures that you're comparing, but simply due to residual bias in your effect estimates, due to model misspecification, we can end up somewhere else and say, well, clearly treatment A is far superior to treatment B, and there's no way we should be giving anybody treatment B anymore because we've shown that it's statistically significant. So this is a situation where even though we're talking about residual confounding, not like leaving out a confounder completely, but just how well we are specifying that model, may have important effects on our conclusions and the policies that result from those. So the other aspect of choosing this effect estimate is what scale you want to report those effects on. And we typically live in ratio land. And ratio land has some really nice properties. Ratio estimates are relatively stable even when you change the background rate of the event that you're looking at, which is handy to say the least. But there are times when it may not be the most relevant scale. So I would argue that a lot of times when we want to look for effect modification, it may be the different scale that we really care about. And rather than pick one of these over the other, it would be nice to get them all. And we can do this now. We can estimate the risk difference. The code we have for doing that doesn't converge a lot of the time. But these estimators, either G-computation or IPTW or the Doubly robust estimator, let you do this suite of estimates simultaneously. You don't have to do a different model. You don't have to fit a different set of parameters in order to get multiple possibly interesting effect estimates. So in the context of that, we measure a 20% reduction in the relative risk. And for men who are very likely to have this event, the background rate is 8%, the background rate is 10%, and you reduce that to 8%. And if you sort of translate that into a number needed to treat, that's 50. I mean, that's fabulous. We should just put it in the water. Everybody should get this. If this is obviously a concocted extreme example, but if the rate is considerably lower in a different subgroup like women, you're not going to get a number needed to treat at 50, even if the relative reduction is the same. So if you can get a 20% reduction, that looks fabulous, and you may get exactly the same effect on the relative scale in multiple populations. But I would argue that we probably want to check the other scales as well and make sure that our conclusions still make sense if the background rates are differing across those populations. So that's one reason why these estimators sort of from the causal inference realm may be interesting to us. So we talked a little bit about choosing the target population before. And so I want to throw this out for a minute. Under what circumstances would we care about the effect in the total population? Just off the top of your head, you have an example of a study that you did where you thought, clearly the relevant population here is everybody. Okay, so Alan says when you're comparing alternative treatments for people who could be candidates for either treatment. Any others? What about when would you be interested in the effect of the treatment in the treated? Go. Uh-huh. So if you were looking at So to reiterate for the folks on the web, in a situation when you're maybe looking at a safety issue and you have a population of people who all got treated, and you're not proposing to treat even more people than already were treated, but you need to know what would have happened to those individuals in terms of this adverse event that you're concerned about had they not been treated. So the population that you care about, or the distribution of covariates that you care about, is the distribution in the people who were treated, not the total population. So in different situations, there are good reasons to choose different target populations. And in general, if there isn't treatment effect heterogeneity, at least on the, no, I'll just stop myself. If there isn't treatment effect heterogeneity on whatever scale you've chosen, these estimates aren't going to be different depending on the choice of the population. But if there is, then as soon as you start changing the mix of who is in that target population, you're going to change the group about whom you can make inference using these data. So of note, what we often do, be it with logistic regression or log binomial models, that estimate that we get doesn't apply to an identifiable population if there is treatment effect heterogeneity. So I think it's safe to say that the quote-unquote one-size-fits-all approach to patient treatment is not really considered viable anymore, and everyone really wants to figure out who are these subgroups who would either benefit a great deal or be harmed a great deal by this treatment, and we want to make better choices on that basis. But that means that we need to be trying to look for this treatment effect heterogeneity. And what is the biggest impediment right now to identifying treatment effect heterogeneity when we do our models? Any votes? how do we do it? How do we look? How do we even check to see if we have different effects in different groups? You need data. That's a good start. Excellent point. Lots of times we don't even have the data. Supposing we might have the data, when we go to do our regression model, we're going to put in an interaction term. And we'll say, look at that p-value. It's 0.3. That means I don't have interaction. Oh, thank God, because I don't want to have to report separate effect estimates for this whole paper. It's going to make me crazy. And heaven forbid you had an interaction between age and sex and race all at the same time. I mean, you would just pretend it wasn't there and you'd go home because it would just make you crazy. So again, my hope is that some of these other methods from the causal inference world will help us be able to investigate these potentially important sources of heterogeneity, and we don't have to give up a summary effect estimate. So we still get a summary effect estimate that applies to an identifiable population, and we can report what's going on in subgroups. That seems like a good idea, at least in my book. So just to summarize how I've been thinking about causal effects in the context of comparative effectiveness research, we're sort of in the perfect storm of having a lot of data, apparently precise estimates. We're interested in small effects that might be meaningfully moved around by residual confounding. We really would love to know if there are important subgroup differences, but we don't want to give up having a summary effect estimate. We really don't want to have to report all of our effects for our analysis in 14 subgroups and not have a summary effect either. And then there's good reason to think that not only relative effect estimates, but absolute measures would be interesting. And the doubly robust estimator can maybe offer some of this, but it's also not going to solve all of our problems. So we still have to specify one of our models correctly. And this augmentation bit only reduces to 0 when we can invoke this assumption of no unmeasured confounders. And worse yet, if we do a really crummy job with both models, we can be worse off than if we had had a single poorly specified maximum likelihood regression. We're going to pay a little price in terms of standard errors, and I think in the sort of realm of big data that we live in, that's not as much of a problem as it is in other areas. It's also a little bit disconcerting that we're still trying to understand how this thing behaves and sort of diagnostically, what do we need to be on the watch for, and those things are still being developed. So it hasn't evolved to the state of knowledge that we have even about propensity score models, and a lot of that work has been done fairly recently. So sort of high-level conclusions. We're in the business of using observational data, and we don't really have a choice but to depend on statistical models to try to disentangle causal effects from confounding. And of course, we're never going to be certain that the statistical model we've chosen is correct. The doubly robust estimate is unbiased if at least one of them is correct, and that gives us sort of a second chance at doing a better job of controlling for confounding. And in my view, I think comparative effectiveness research is an area that might be particularly benefited by this method, and others like G-computation, IPDW estimators that share some of its other nice features. So I'm happy to open it to discussion at this point, and I know that the people online will be able to and want to jump in as well, so we'll do as much of discussion here and also pull in the people on the phone. Liz is in charge. If you'll please go ahead and use the mic.
Hi, Michelle. John Sager from Brigham Women's Hospital. Very nice presentation this morning. I was curious on your slide 74, where you have the different estimates, the crude, the maximum likelihood, propensity score, and then the doubly robust. And your question about how do you know which is right, and was wondering if there were some other approaches that you might be able to explore about ways you could investigate which one to settle on.
Yeah, the folks on the web hear the question, Liz? Yes, they can hear from the mic. So one proposal that actually comes from Robbins et al. Is to use this as a way to try to calibrate your model. So potentially you build a propensity score model and an outcome regression model separately, and then you put them into the doubly robust estimator in the same form, and you see which way your doubly robust estimator is leaning. And if it's, this is very much in the, maybe that would work realm of Jamie Robbins. So there isn't a nice analytic proof that says, yes, if you can move your propensity score model such that your doubly robust estimate and your maximum likelihood estimate all start to converge, that you're in the happy place where now your maximum likelihood estimate is good, and you can ditch the extra standard error penalty that you just paid. This is also going to touch on sort of the multiple testing bone that might start to twinge a bit. So this is a model selection process now, and you're looking multiple times to see what's going on with your estimate. And you really can't do that without paying a penalty in addition to just the penalty that we've already seen. So that's not a fabulous answer to your question, but that's kind of the state that it's at right now.
No, thanks. I was actually thinking also from a angle that I've encountered in this setting was trying to consult experts, topical experts, with respect to sort of biologic mechanisms, the expected time course of events, looking at survival curves and seeing if they diverge immediately or if there's a lag sort of in expectation of the effect of the medication or treatment, whatever it happens to be.
You talk to clinicians? What? Yeah. So, this is definitely the point where you can't just go into a dark room with your computer and put things in and get numbers out and be in good territory. You absolutely have to look at the effects that you're getting and the individual parameters on the effects that are in those component models and try to understand if you're really, does this make sense clinically? And if it doesn't, I would not, I would start from a prior that, well, clearly what I've done is innovative and brilliant and it must be published immediately. It's time to run back to the hospital and talk to somebody who knows more about it than I do from the patient perspective. Good. You mind using the mic so the people on the phone hear? Just pull it over to you.
Can you hear me?
Yes.
Does it work? Okay. Now, just a few points. One, we talk here about comparing. I just take it in my hands. We're talking here about comparing, for example, a G-computation or maximum likelihood estimator versus maybe an inverse probe sensing treatment-weighted estimator versus this double robust estimator. For example, there is an estimator which actually is all three of them, right? So there isn't. I might touch that, but not necessarily. Okay. Yes. So, for example, there's a target maximum likelihood estimator, which is both. It is an inverse probe treatment-weighted estimator. It is a G-computation estimator, and it is a double robust estimator of the type presented here. So then you don't have to worry about the choice. It's all three. But the other thing is, what I hear a little bit, just to start a little bit of an argument with you for the sake of discussion,
of course,
is that I hear a little bit you're saying, oh, yeah, we need to look at these models. We need to look at these coefficients. We need to make sure they make sense. Let's go back to if you are running a phase 3 clinical trial and you want to get your drug approved, right? I mean, the FDA wouldn't allow that, right?
True.
So in other words, the point I'm making here is that any analysis has to be a priori specified. And I'm arguing that we should have the same standards for any kind of observational data analysis, such as in safety analysis, as we would have for a randomized trial. And I think by setting that standard, that you have to have a priori specified estimators, right? Because otherwise what we get into is we are going to look at this 200 million patient database. And as you pointed out is that a small amount of bias can easily transform one conclusion to another. And that can have dramatic effects, right? So there is a lot to say for having an objective method, which at least doesn't suffer from the usual bias due to trying things out and whatever reasons the person might have. And that's the very reason why the FDA doesn't approve drugs based on just playing around with the data, right? It has to be a priori specified. So I think we need the same a priori specified protocols. However, once you do that, so once you are going the route of saying, yes, we need that, we need an a priori specified plan, you start becoming very susceptible to methods which rely on machine learning. Because suddenly a method which relies on some kind of parametric regression model, right? And when you apply that, don't be surprised you're not going to like your answers. And then you say, let's try maybe to add a few interactions because maybe that's what's going on. But you don't have that room. You get only one chance. Okay? And so that's what's. And anyway, that's why we have, and I will talk about that tomorrow. That's why we have proposed indeed the single system, which we call superlearning, which allows you to a priori specify all the things you want to try out, but they are still part of a single estimation procedure, so that it is allowable and it's objective, and the uncertainty gets carried through. So that's one point. Maybe you can respond to that.
So I don't think Mark introduced himself. Mark van der Laan. And so I think my personal perspective is that I'm never going to report a single estimate. And so by reporting a range of estimates from trying to understand the data using different approaches by including different covariates, I'm not going to be able to give you one number, which would be very dissatisfying to FDA and the drug companies that need to get their drug approved. So I would agree. In that realm, my approach would be incredibly unpopular and wouldn't last long, or didn't last long. I think from a sort of observational data perspective, I feel more comfortable trying to understand and not really thinking that I'm ever going to give you a single perfectly best accurate answer, but that maybe by digging into the answer that I got and trying different approaches, I'll come to understand why it is that it's doing different things. So I think in different settings, our approaches, I hope, are complementary, and I would love to try out the super learner. So we have to sit down and play on your laptop later and try it out. Yes?
First, I'd just like to congratulate you on a very clear presentation
Thank you.
on double robustness. Just had two very basic questions as far as the rationale. So first, with estimating the propensity score and making sure you have a good model fit, at least what I've learned in my classes is that you want to make sure that you can have good overlap. And if you predict the propensity score too well, then you have less overlap and have less common support. But in this method, we're comparing our estimated propensity score versus the true propensity score. And so, but we still want an amount of overlap, which means that we don't want to perfectly predict the propensity score. So there's an inherent level of measurement, or at least that's what it seems like to me. How do you?
I think I may have this may be a terminology problem on my part. So when I said that your propensity score model was misspecified, that pertains to well specified in order to control the confounding that you're worried about or that exists in your data. And so I think we're in the same boat still. We're just not only having to do it on the propensity score side, but now also understand how that model fit behaves on the outcome regression side. So I think we agree.
Gotcha. Oh, it was just a question, not a debate. The other question I had was about effect modification and modeling that in your outcome model versus your propensity score model. Do you?
Boy,
because that's, that would be a source of misspecification in the outcome model. And
that is not a trivial question. So this is off the cuff because I actually am in the process. We put in a grant last week trying to develop methods better building on these to think about how to assess effect modification when it's there. So that said, gut check, I probably would not go looking for interactions on the propensity score side. I would put them in on the outcome regression side. But I can't really, I have no data to back that up right now. That's at instinctual level. Does anybody else have actual, data or a better gut check than I do in terms of finding effect modification?
Maybe I didn't understand the question. Were you saying you don't, I thought the implication of what you said in your presentation, and I would agree with it, is you want to correctly specify the model for the propensity score, and if the correct model has interaction terms in it, you're better off. But I may have misunderstood the question because I didn't hear the beginning of it. So
I think the fact that we use interaction terms to identify effect modification and to potentially better identify subgroups where our confounding effects differ, I think those two things intersect here are a little bit hard to tease apart. So if the thing that we're talking about is truly just an effect modifier and doesn't actually change the channeling of who got the drug, then I think you would want to have that in your outcome model as flexibly as you could so that when you started looking within subgroups, you would be able to see whether or not those outcomes differed by those subgroups. But lots of times the things that we think about as potential effect modifiers are also confounders. And so in that sense, I would want to see it on the propensity score side as flexibly as possible to make sure that in my overall effect estimate, I'm controlling for any imbalance that comes from that. But again, this is coming from a sort of a gut feeling place, not I ran the simulation and I can tell you for sure. So
does it follow, maybe I didn't understand, does it follow from what you said that you want to correctly specify the model, but you don't want to include instruments? So you're
correct.
Saying if these interactions were irrelevant to the outcome, then you don't want to include them? Is that
yes.
a fair way to make it
yes.
consistent with what you said earlier?
Yes.
And along those lines, there's a...
Sorry, all right, let me just make sure. Did we get...
Thank you.
That's okay. I'm glad that it's a discussion, not just...
Yeah, in the spirit of discussion, I just wanted to follow up a little bit this issue about when you're trying to correctly specify these two, the propensity score and also the model for the outcome, you're not in a totally analogous situation because when you're trying to correctly specify the model for the propensity score, you want to leave out instruments, as you put things that aren't related to the outcome. But when you're trying to correctly specify the model for the outcome, you don't want to look over your shoulder and leave out things that are unrelated to the treatment. because you'll improve your precision if you include them. So you're not in an exactly analogous situation trying to wind up with the same set of variables.
That's a good point. So if there are things that are truly only risk factors for the outcome that have no real-world causal relationship with your exposure mechanism, then I think it should go in your outcome model. It's probably not going to hurt anything to put it into your treatment model because it's not an instrument. It's not actually going to pull apart your propensity score curves and increase the degree of non-positivity that you're facing. But I think you're right that this isn't, it's not as simple as saying everything in the same place, and I need to think about that some more in terms of where are the, particularly with respect to things that have this asymmetric relationship that are drivers of the outcome but not at least causally related to treatment, and then also in the context of effect modification. There are things that you would want in that outcome regression model to make it flexible, but that wouldn't necessarily be helpful in your propensity score model. Mark?
Yeah, I think... hello?
I think you're there.
I'm there? Okay. I think they're actually pretty analogous, the two, in the sense that, I mean, there are a few things you need to know. One is that when you start estimating, when you start including in your propensity score covariates which have no relation to the treatment, but you still include them, right? Because, and there will be some empirical association. They will actually improve the efficiency of the procedure, right? So that's one thing. So so that means putting these covariates, which are not really confounders, in other words, they are not associated with the treatment in truth, but they are related to the outcome. They are helpful in both the outcome regression model as well as in the treatment model. And you can argue theoretically that you should include them in both, because they, you might get the outcome model wrong, and then they still improve efficiency through the treatment model, and vice versa. The other thing is we're talking about variables which have no relation, which have an extremely strong relation to treatment, but no relation to the outcome. So, like instruments, they are particularly bad, indeed, in the propensity score model. So in that sense, yes. Because why? Because they are using in this inverse weighted way through these double robust estimators. But they are bad also when you fit an outcome regression model, because we get some kind of almost collinearity, and it creates a lot of instability in that sense as well. So they're bad in both ways. But anyway, this also hits, of course, an incredibly important point, is you might a priori know that certain variables have no relation to the outcome. Now, good. Get rid of them, never consider them. But then we are getting in the situation that we are still having 500 variables left, and we have no real idea. Many of them might indeed be almost like instruments, but we don't know. And so this is a very challenging, actually, problem, right? I mean, how are you going to fit the propensity score and in the outcome regression model in whatever double robust procedure you use?
Whatever procedure
you use, because of this fact that you might, when you do any kind of automatic selection, that you might select variables which are like instruments, and just starting to look at things, okay, this looks. We get into a very ad hoc stuff. So there's actually a real challenge here.
I don't disagree.
But it's the way we have attacked this challenge is through this collaborative target mix and light estimation, by recognizing that the goal is not to fit the propensity score model. The goal is to use the propensity score model to remove bias for your parameter of interest. And so that we should have a loss function criteria for selecting variables in the propensity score model, which is measuring the performance for your actual parameter of interest, right? Your causal effect. And so that means the criteria is then not going to be how well you fit the propensity score. Right. No, it's how good is the propensity score in actually removing bias for your parameter of interest. And so that's But it's a challenge. Yeah.
Amen.
Yeah.
Let me take just a second and see if there's anybody sitting on the web thing that has anything that is queued up. It's fine if they don't. I just don't want to be ignoring them.
Yeah, there's one question which may have been touched on a little bit. They ask, should we select different sets of covariates in the propensity score and outcome models when fitting the doubly robust model, since we have two chances to get it right?
Per mark, if we think it's a confounder, we should put it in both places to the best of our abilities. And I don't know that we will do better by intentionally doing a less thorough job in one model than the other. So I would, again, my approach would be to try to do the best job I could in both models, and that may or may not mean that it's in there in the same model form. It would depend on what the relationship, if it's a continuous variable, it might depend on what the relationship is between age and the outcome, which might not be the same as the relationship between age and the treatment selection. So.
Yeah, I'm Philip Cottrell from CMS, and my question goes to the issue of the unmeasured selection bias. And because I've been involved in some work where we model both selection and outcomes, but by using the bivariate probit model, we get an estimate of selection bias as well. And so, I guess I'm just curious what you think about. I mean, the standard criticism of the bivariate probit is that you would have to assume that the errors are normally distributed for both selection and outcomes. But, you know, you can do some things to try to, which we did in a paper, you can do some things to try to increase the probability that your errors are normally distributed. And then you do have the advantage that you learn something about the magnitude of your unmeasured selection bias, because it, you know, the parameter estimate is a measure of the correlation between the errors in the two equations.
So this isn't something I'm familiar with, but you've piqued my curiosity. So well, I want to learn more later.
When it's coming out, but we have a paper that will be in Medical Care, and the lead author's A. James O'Malley from Harvard, and I'm the second author, and we have other authors.
Oh, great! Thank you. It looks like we wore everybody down finally. I am not going anywhere. We can let the people on the Internet have a break. I think the afternoon session will start at 1, so they'll have a nice long lunch. And I will hang around and we can have some more informal conversation, but I really appreciate all of you coming and being engaged. I know this was not light fare for first thing in the morning after flight. So thank you very much for coming.